Welcome to Ask and Learn.
Okay, so this question is asking us to verify that the function f of x equals 2x squared minus 4x plus 5 satisfies the three hypotheses of Rolle's theorems on the given interval. And then we have to find the number of c's that satisfies the conclusions of Rolle's theorem. So here we know that f of x equals 2x squared minus 4x plus 5. So just by looking at this function, we know it is a polynomial because it has a function of degree greater than 1. So here it's 2. So we know this is a polynomial, and all polynomials are continuous, and they're also all differentiable. That is a property of all polynomials. So we know off the bat that these two conditions, continuous and differentiability, are a given of a polynomial. And if you actually plug in the values of -1, so if you plug in 2 of -1 squared minus 4 times -1 plus 5, you actually get 11. And if you do the same thing for 3, so now you plug in 3, so 2 times 3 squared minus 4 times 3 plus 5, it also gives you 11. So we know that f of -1 and f of 3 are also satisfied. It's also a true statement. So now that we've satisfied all the three conditions required for Rolle's theorem, we can go ahead and find the numbers of c's that satisfy the actual conclusion. And so to recall, the conclusion of this theorem is that we know that there will be a number c in the interval such that the derivative at point C is equal to 0. So we have a horizontal line. And we can actually solve for this in this case. So if we take the derivative of f of x, so the derivative of f prime of x, which is just the derivative, we can find that the derivative of f of x is just 4x minus 4. And all we're doing is looking for where this function is equal to 0. So all we do is set this function equal to 0. Then we just bring the 4 to the other side. So we get 4x equals 4 and x equals 1, and solve for x. And this is also our number c, because if you plug in this value 1, so 4 times 1 is 1, 4 times 1 is 4, minus 4 is 0. So that is the c that satisfies the conclusion of Rolle's theorem. So here's our answer.